And so if you are at home, I've got a sheet linked out for you just on my calendar. Click on today, applications of quadratics. Just click the notes right there, and you'll get a PDF of everything that we're going to do today. Got some notes and some practice problems for us. So it's not really anything new. We're just going to take a look at what are some actual uses of parabolas. Like, why would it be important to know what the vertex is or things like that? And so that's going to be our goal for today. So if you're at home, go ahead and pull that up. Everyone, make sure you get your graphing calculator out or your Chromebook with that TI-84 app on it, all ready to go as well. And let me just do a quick sweep of the room. Make sure we are all here. I think we're good. Cool. All right, so I also have some really good news to share with everybody. Are you ready for this? I got a 90-day demo, okay, of something new that I'm pretty sure that this is going to be a worthy investment for the school. But take a look down here. It's called TI Smart View. You remember my crappy calculator that I had before to demo that just didn't do anything? Well, I got something pretty fancy now. I'm very excited. It's just a demo. 89 days left. Started it yesterday. Should get me through the week at least. But you're going to be blown away. This thing is amazing. It makes me so happy. Like, I just played around with my online graphing calculator yesterday. Look at how large that is! What? Isn't that cool? Now check out all these features. Ready? I can, if I hit a button, look, it highlights it in red. So like if you're watching, you can see, oh wait, what did Wojcik just press? Or if I say, 9 times 6, enter. Oh, thank you, Vegas. Yep, I'm not sharing my screen. That's awkward. Good call. Good virtual students. So yeah, look how cool this is. When I said y equals, then you type in, x squared plus 5x. You don't actually have to do this right now, minus 6. But look down here. It even shows like the buttons that I pressed, like the history. So if you're like, wait, how do you get there? You can just follow along down at the bottom. Be like, oh, he hits this, this, and this. What? And then graph it. Isn't that great to see? Pretty handy, right? I wish I had this years ago. But it should be pretty useful for today. So if you're still a little rusty with finding like the vertex or the intercepts, and today we're going to add one more thing that we can find on the graphing calculator. We have this wonderful program to show us how it works. And I mean, I can even change like the faceplate. Instead of a light, I could have like the dark mode. Ooh, it's fancy, right? Pretty groovy. Or the model, just like the regular basic version. If I don't want to show off the colored one, here's just your general one. Boop, right there. Basic line. So I'm pretty excited about this. It should help teaching really nicely. I can switch which side it's on. Oh, look at that. It's like I'm juggling. Okay, I think I've wasted enough of everyone's time so far. And let's jump into a little bit of learning.
We have more than you can.
I know. This actually wasn't that bad. So today we are going to just practice quadratics, but we're looking at, when would I actually use this stuff? Or how can I actually use a parabola to determine some relevant info? So yeah, you can just write on here. I don't think you'll need a notebook for this, but I did hole punch it for those of you. Let's keep things organized. You're welcome. And so I've got two. There you go. So I've got two problems for you that are really broken down on this sheet right here. And so we're going to take a look at this. And here's the idea that's going on. You got a guy kicking a football. And when you kick a football, or when any object goes into the air, because of, what's that thing that pulls us back down to the ground called? Gravity. Yes, you're so smart. I love that. And so because of gravity, when something goes up, gravity pulls it right back down. But as it's going up, gravity's still pulling it down. So it doesn't like go up forever. You know, it's not like a straight line. It's going to go up, but it's going to go up lower, lower, lower. Eventually it's going to stop moving upwards because of gravity. It's going to start coming back down. And it's going to land somewhere. And the path that that ball will take in the air is a parabola. Right? That's the way that gravity affects any object in the air because of acceleration. It's accelerating it downwards because it's a force. I know, all kinds of physics talk, right? And so we've got this equation right up here. And is that a quadratic equation? Do you think? What's the one thing in there that tells you, yeah, that's definitely a quadratic equation? The x squared, right? You see that there's this x squared term right there. So that's what makes it a quadratic. That gives us that parabola, that parabolic U shape. Okay, so this is a quadratic. It's just got, a decimal. It's kind of gross, but it doesn't matter. We're not actually working with that. So we're just going to use the calculator. So we're cool with using decimals today. And so the kicker's kicking the ball. Someone's trying to block it. And we're just going to analyze the path that the football would take flying through the air. All right. So here we go. A. What is the maximum height of the punt? Well, as I just mentioned, this is going to be the path of a parabola. And what you call that highest point on the parabola? The vertex, right? So essentially, the maximum height of this punt, what it's really asking for is, hey, what is the vertex of the parabola? Do we know how to identify the vertex of a parabola? Of course, that's what we did yesterday, remember? On the calculator, the left bound, right bound, yes? So, let's take out our graphing calculator. I'm so excited I get to use my new smart calculator program. And we're going to type in this equation right there, okay? So, everyone grab out your graphing calculator. You're going to go to y equals, clear that out. Whatever's in there, just press clear, which you can see because it's highlighted in red. This is so cool. Oh my gosh. And we're going to type in, now this is a negative 0.01. Remember to hit the negative key down on the bottom row of keys. Do not hit subtraction for this. Negative 0.01. X is the button right next to alpha squared. And then plus 1.18x plus 2. So this is what you should be typing in. If you're not sure what button to press, they're all listed right down here. Oh my gosh. So fun. If you want to play around with this after school, feel free to stop by and we can just graphing calculator all afternoon for like hours until we get hungry for French fries. Then we'll need to take a break. All right, so you got the equation typed into y equals to y1. Make sure nothing else is typed in. Make sure none of these plots are turned on. None of them are highlighted. They shouldn't be. I think we took care of that yesterday. And now hit the graph button. Oh. Uh-oh. Is that a parabola? Definitely not. It is not a parabola, right? But we know it should be because we have this x squared. This is just our window is like zoomed in too closely to it, right? We need to kind of take a step back. So we want to change the window. Remember like the x min, x max, or y min or y max. And in this case, since we're starting like right here, we're going to be in quadrant 1. For most of these word problems, we're always going to stick in quadrant 1, which means I need to look more to the right and I need to look up more, right? Because I know the vertex is going to be up higher somewhere. So what we're going to do is press the window button and we're going to go down to y max, which is only at 10. Let's make that a little bigger. Maybe go up to 50 and hit graph. Okay, so now I think my y max, that's high enough, right? But what part of the window do I need to increase now to see my vertex? Yeah, that x maximum, because I want to go to the right. And so right now my maximum x value is still a 10. I need to make that a bigger number. So I'm going to go back to window. And there's x min. Go down to x max. And that's only at 10 right now. but it's going to be something bigger. Let's also just make that 50. And I'm just trying, a little bigger number. Then I try a little bigger and keep on making it bigger until you try to finally find what we're looking for. All right, so I went to 50, and that looks like maybe half my parabola. And so 50 is not good enough. What number should I try next, do you think? How about 100? Yeah. And the exact numbers that you're typing in for your window, it doesn't really have to be exact the same thing that I'm doing. All right, we just want to see the parabola. All right, I can see the vertex, but I can't see the other x-intercept. Generally, whenever you are looking at your graph, we're going to want to see the vertex and those intercepts. So I'm going to change my window and x max. I'm going to maybe make this 200. Dun, 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 dun. Yeah, or 250 is fine. Maybe even 180 would have worked, but this is good enough for now, right? Can I see the main parts of the parabola that I wanted? Yeah, that's fine. And if you don't have this exact picture, if you didn't use the exact values that I did for my window, that's totally okay, because your vertex and your intercepts will still be the same no matter what window you're looking at. You could be zoomed out further or zoomed in closer. So like, see how this x-intercept is really close to the left edge of the screen? Maybe I want to change that so I can make my x min, instead of negative 10, maybe make that negative 50. And there, see how that kind of pushed this over to the right more? So that works a little bit better. Now, do you see those little tally marks, those little hash marks that are like really close together on my y-axis? And on my x-axis, look, they're so close together, it looks like a giant block. If I go to window, there's one option that I didn't really talk to you about, XSCL. That's the X scale. Basically, that refers to how many numbers each little tally mark is. So I could change this to like 20. And so now every one of those tally marks represents 20 units, right? So it's going like 20, 40, 60, 80. Do you remember when we did that with like linear programming? When we scaled the axis, we would say, oh, make every line be like 10 or 50 or something like that. Same idea with the graphing calculator. So maybe for the x-axis, I don't like all those lines together, or I'm sorry, the y-axis. So I'm going to change the y scale, YSCL. It's at 1 right now. Maybe I'll make that 20 as well. And there we go. Now I can see my parabola. Just make sure you don't count these as like 1, 2, 3, 4, 5. Be like, oh, that's only that football punt has only gone 6 feet. I hope it's gone a little bit further than that. So we've got our parabola. Now let's go back to the question. All right, so we want the maximum height of the punt. So this line basically represents the path that the football would take up into the air and then back down, hitting the ground somewhere down the field. I want to find the maximum height. Well, that's right up top here. That's essentially the vertex. So let's go over how to find the vertex. Press second trace. That's going to be our main menu we're going to go to for almost all of these, and that's the calculate menu. And which of these options do I select to find the vertex in this case? The maximum, right? Because like there's a maximum part of my parabola before it starts going back down. There's an absolute top to it. It's like a hill. So I'm going to go down to option 4, which is maximum, and hit enter. And I've got my cursor there. And remember, make sure you only use the left and right arrow keys whenever you're moving the cursor. And it asks for the left bound or the left boundary. So hit the left arrow key until it's to the left of the vertex, and you press enter. Then you press the right arrow key till it's to the right of the vertex for the right bound or the right boundary. Press enter. See how it even adds in those lines, and it says basically it's going to find the highest point between those two arrow keys, which is perfect. That's what I wanted. And then for guess, just get it somewhere close. This does not have to be exact by any means. But then when you hit enter, it'll tell you 59. You can ignore all those point zeros. And 36.81. Right? That's the coordinate. That's the ordered pair on my coordinate plane where the vertex is. But this question asks, what's the maximum height of the punt? Would I write 59, 36.81 for the maximum height? Would that make sense to have two different numbers for my height? No, not really. It should be just one number. But the important part for you to interpret for this problem is which number is the height? Is it the 59 or is it the 36.8? So if we think the first coordinate, the x coordinate, that's left and right, that's like distance down the field, right? Like that's how far down the field the ball went. The y-axis is always our up and down. So that would refer to the height. So I want the y coordinate here, which would be this 36.81, right? So the y coordinate is the height of the football, and that's the highest point that it'll ever reach. So it's getting higher and higher, gets up to 36.8 feet, and then it will start to come back down to the ground. So over here, maximum height, and this is in feet, so we can say 36.81 feet. And since these are word problems, we're going to make sure that anytime we write a number down for an answer, we include the units with it. So at 36 feet, that's the highest point that the punt went, the highest point that the ball went in the air. All right, the next one is actually kind of related to this. It says how far down the field, okay, so how far away horizontally from the punter did the ball travel when it reached this maximum height? Well, do I need to recalculate something to answer this part of the question, or do I already have that value?
You already have it.
Sure do. So how far down the field did this ball travel? Yeah, it's that 59. So on that x coordinate, that refers to how far down the field the ball traveled when it hit that maximum height. So for part B, we would say, hey, it's 59. That was 0.0000. That's pretty much just 59 feet. Yeah.
I got 58.9.
With a whole bunch of nines?
Yes.
So since it's so many of them, that's just like a rounding error. 0.9999998. That's actually really, 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 really close to 59. So we would just say 59.
Oh, okay.
Just like on mine, if you notice when my calculator calculated, see how it's 59.000001?
Yeah, I was just saying that because it didn't match on things just
Yeah, so those are both off by such a small amount that we would just kind of ignore it and just say, okay, what's the whole number that it's closest to in this case? All right. What do you think? We understanding this so far? It's not too bad, right? Okay, so the nearest defensive player, so that's the person trying to stop this guy from kicking the ball. So that player can jump up really high and reach a height of 7 feet, right? So he's trying to block the ball. He's going to jump up in the air, and he can get a total of 7 feet high, like with his hand, to try to knock that ball out of the air. So how close would that player need to be in order to block the ball? So what this is asking is, we know that this ball is going to travel something like this, right? And this person right here, he's got to be a certain distance. He's got to be kind of close to him, because obviously he's way out here. Well, this is way too high. Dude can't jump that high to block the ball. But the closer this guy is, well, then the lower, the lower the football will be, the closer he is to the punter. Right? If he were standing right in front of the punter, wouldn't be an issue. He could just go like this and he'd block it. Put his hand right down at the ground. But he's running up to them, and we want to know, okay, what's that distance where he would have to be, if he can reach 7 feet high. So it's basically asking, okay, if this is 7 feet, if that's the height, and the ball is at 7 feet in the air, how close is this? So like at this point right here, that's this vertical distance of 7 feet, right? So this is 7 feet high. Then what I want to know is, what would that horizontal distance be? Like, how close to the punter would he have to be when the ball is basically 7 feet in the air? So this is actually going to be a new skill that we didn't actually look at yesterday. And if I look at this equation here,
No, it really is physics.
it is physics. I know, it's so good. I've got two variables. There's the x variable, and then there's this h variable. Now the h is actually the y, because that's the height of the ball. And I want to know, basically, what is the x, what's that horizontal distance that the defensive player's got to be when the ball has at a height of 7 feet. So essentially, I'm asking when h right here is equal to 7. right? So if this is 7, what would x have to be? Now, we could solve this as a quadratic equation, but no, we've got technology, we've got a calculator to do it for us. So here's what we're going to do. I need to find when y is 7 on this parabola. Now, we could just kind of, if I hit trace, I could move the cursor and try to get it to see, okay, when is y close to 7, but it won't be exact. So here's what we're going to do instead. Let's go back to y equals and go down to y2. So we're going to make a second equation, a second line. And this line is just going to be y equals 7. Because isn't that basically what we wanted to know when the y value is a 7, when the height is 7? So I'm going to make a separate line that indicates where that 7-foot height is. So now when I graph it, see that red line is the 7-foot height. So basically I want to know, okay, what is this point right here? Because that 7-foot line, that red line, it's going to cross my parabola right where I want to know. Okay, well, that's going to be my point. That intersection point of these two lines would give me, the y value is 7, and that x value of the intersection, that's going to be my answer. That'll tell me how far away this defensive player needs to actually be. So now we need to find the intersection of two lines, and this is a new skill on the calculator that I'm going to show you, okay? Luckily, to do this, we go to that same menu we've always been going to. So press second trace, and you see an option on here that can help us find the intersection of two lines? Just give up, right? There's nothing here that indicates an intersection.
Oh, it's minimum.
Minimum. I don't know. Maybe we'll try this one that's intersect. It's close to intersection, but not exact. I think it might work for us.
I can't get like two lines to line. Like every time I activate this line, that line turns on. And then every time I turn on that line, I tried hitting lots, I tried everything.
And so it only grabs one time.
Yeah. It used to grab one of the one.
Just do a quick reset. Try typing them back in right now. Should be good to go. Yeah. Grab the other one. Mike. You were just zooming so far out because 7 is a pretty small number, right? And your window went from -150 to 150, so that was a range of 300. And your line was only 7 above the axis. It just couldn't see it. You were too far zoomed out. Is everyone else able to see the parabola and the horizontal line on your calculator? Was everyone able to do that? Okay, so you select intersect. Press enter. And all right, we have some different questions now. It's not left bound, right bound. It says first curve. Now, as I mentioned before, typically we always just press left and right to move the cursor along one of our lines, one of our equations. And so it should be on whatever y1 is. And at the top of your screen, it will tell you y1 equals, and it should show you the equation of our parabola. And so first curve just means make sure the cursor is anywhere on the first line that we want to find the intersection of. So if it's already on here, just press enter. And look how my cursor automatically jumped to the other line, to the other equation. And now the question says second curve. Now I know that this line isn't really curved, but that's just the word that's built into the calculator for any equation. And if I look in the top left corner of the screen, it should also say y2 equals 7, because that's when we typed in our second equation. So second curve, hit enter. And then guess just means we need to move our cursor to, close to the intersection point. Because in all honesty, how many intersection points are there for this parabola and that line? Give you a hint. It's more than 1 and less than 3. Yeah, there's 2. So the guess here actually is important because I have to indicate, hey, which intersection do I want to find? Because I can find the intersection on the left or the intersection on the right. Well, we want to find the left one, right? Because that's the closest to that defensive player that we're trying to identify. So hit enter, and it says that the intersection of these two is at 4.4, 7. Now, should we have had a y value of 7? Is that what we were expecting? Yeah, because remember, that defensive player can reach up 7 feet high. And that 4.4 is telling us that when the ball traveled like 4 feet away, it would be up at a height of exactly 7 feet. And so that's telling us, all right, so this guy right here that can jump 7 feet, he's got to be at 4.4 feet away from that punter or closer, right? Because if he's closer, the ball would still be a little bit lower, closer to the dude's foot that's kicking it. But if it's, say, 5 feet away, then the ball will be too high. The ball will be greater than 7 feet high, and the guy couldn't jump up to try to block it. Are you kind of seeing this, visualizing this a little bit?
Oh, yeah.
Does it help when I jump off and stuff like that to
Yeah.
indicate what's going on? Because I'm such a big football player. Oh my gosh. All right, so back to part C. How close does that player need to be? So we're basically looking at the x coordinate here, right? That's the x coordinate when the y coordinate was 7. The x coordinate was 4.4. So that tells us that's that horizontal distance. That's how close that defensive player would need to be. 4.4 feet. As long as that defensive player is 4.4 feet or closer, we know that he'll be able to jump up and block that ball. Now, what if that football is not blocked? Then how far down the field will the ball travel? So essentially, we know that we've got this parabola. Here, let me clean up our little picture. And if the ball goes up, we want to know, all right, where's it landing? So we're going to find, what? If I look at my graph, what do you call the point on a parabola where this football would land? What part of the parabola is that called? Can we see where the football would have landed based on this drawing? What do you think, Ben? Perfect. Yeah, the x-intercepts, because this x-axis is basically like the ground. And if this is where the football is going up, there's its highest point, and it's going to come back down. Right here, it would hit the ground. Because what's the y value right here on the x-axis? It's 0. And now remember, for this example, that y-axis is the height. So if the y is 0, that means the height is 0. And if the football is a height of 0, where's it have to be laying? Right on the ground, right? Could the football go down here into like negative 20 or whatever? Would that make sense for it to have a negative height? Probably not. Right? It's not going to go through the ground. Hopefully not. That'd be crazy if it would. It'd make the game more interesting, I feel, if the ball could go through the ground randomly. That's just stupid. I'll stop talking now. All right. So we want to find this point. But wait a minute. There are 2 x-intercepts with this parabola. Just like, usually we get 2 answers and we solve it. Does it matter which x-intercept we're solving for, or is there definitely one that we want to find for this question? There's definitely one. Which one do we want? The one on the left or the one on the right? The one on the right, because isn't that the end of the ball's path? I want to find how far down the field this ball flew through the air when it hit the ground. All right. Now, we don't need this horizontal line anymore. So if you want to get rid of it, just go back to y equals, jump down to y2, and I can either hit clear, or if you press this arrow key over to the left and it highlights the equal sign, I can hit enter. And see how that equal sign isn't highlighted anymore? It's basically like turning off an equation. So if you ever have multiple equations in here and you don't want them all graphed at the same time, you can just turn it off and then turn it on later if you want. So let's go back to just our parabola. So it keeps it a little bit cleaner. And I want to find this second x-intercept over on the right. So to do an intercept, we press second trace. And which option was it for x-intercept again?
0.
The zeros, right. A zero is another word for an intercept because that's where y is equal to 0. Awesome. So we go down to 0, hit enter, and we've got the left bound, right bound again. Now, before you even answer those questions, just press the left and right arrow or right arrow keys until you get the cursor pretty close to the intercept that you're trying to find. And make that like your starting point before you even read those questions that it's asking. Okay, so I'm right near that right intercept, and it asks me for the left bound. So to get the left bound, see the word left there? That tells you which arrow key you need to press, the left arrow key. So don't worry about the cursor being up or down like for left bound, because for this intercept, it would be the opposite. Left would be lower. From this intercept, left is higher. So don't think up and down. Always think left and right for your intercepts. So left bound, hit enter. Right bound, press the right arrow key until your cursor crosses to the other side of that x-axis. Press enter. Guess, get it somewhere close. And we've got 119.7, comma 0. Does that y coordinate sound right? Should we get 0 for y? Yeah, because what did y represent in this example? That's the what of the football? That's the height. Should it have a height of 0 when it hits the ground? Sure. And so that means this x coordinate is the horizontal distance. It went down the field 119.7 feet.
So I got the same thing by doing this. I said y equal to 0.
Yeah, that works. So Brenna, she changed her y equals 7 line to y equals 0, and then found the intersection, which is perfect because that's what the intercept is. It's the intersection of the parabola with the
I don't know if it's because it's just like part of this time or what is the height of it? Like if it's all the same height, I'm not this is not much.
Oh,
I don't
so
know.
the 59 you mean?
Yeah. 'Cause it's like-
Okay, now we're getting into some physics. This is awesome. So Gavin asked a really good question. He said, hey, wait a minute. If we already know, this is pretty cool. He looked at our answer for part B and said, wait a minute. We know that the ball went 59 when it was its maximum height. So wouldn't this just be twice that number? Our parabola is symmetrical, like does the left side match the right side perfectly? And it doesn't make sense that if it took 59 to get here, it would take 59 to go there.
Yeah.
That does make sense, doesn't it? If I multiply 59, do we get 119?
No.
We don't.
We have
118. It's close.
Yeah. That's why it's such a dumb.
Anyone have any idea why that is? It's not a dumb question. It's actually a good point to it.
Is it rounded?
It's not a rounding issue either. That should work. Half of the distance to the vertex is half the distance to the other end. But take a look.
Looks like parabola is doing something.
At our parabola.
Oh, it doesn't start at 0.
When the punter kicks a football, is the ball starting on the ground?
No.
No, it's not. Right? When he's punting it, he's holding it in his hands and drops it, right? So at the start of that punt, the ball isn't on the ground. Is it pretty close to the ground though?
Yeah.
It is. And is 118 really close to 119? Right? Our double number was really close to the calculated number. And so the reason that it's not exact is because the parabola the ball didn't start perfectly on the ground.
Is that just the 1.18x?
It's plus 2. That's the
That why?
It's because Brenna caught it. It's because of the +2. It's the last number.
Got it.
This constant +2, remember, we always call that the y-intercept. And so +2, like if I plugged in zeros for x, we'd be left with y equal 2. That's exactly right.
So if it started on 0, could you do that?
Yes, you could. So if this parabola started at 0, if there weren't a y-intercept, then it would work out to be exactly double. The distance to the vertex would be exactly the distance to the other one. But because we started a little bit higher, it's not actually symmetrical. It's a little bit less to get to the vertex, a little bit longer to get from the vertex back down to the ground. Awesome questions. Oh my gosh, you definitely go talk to Mr. Hellman and be like, we did so much physics today.
I don't want to talk
All right, sorry.
about it.
Oh my gosh. All right, so how far down the field we had? Oh boy, now I got to go back.
119.7.
Oh, I got to change my window.
119.671.
That's how I got it.
Yeah, that's why I rounded to
250.
You can just put for your x, you can just put 125 and it'll work.
To find both of them? Oh yeah, that makes sense because it's at 119. Y max, 100.
Y max of 100 is too much. Put like 40.
Well, it still works.
I know, but it'll be a lot easier on your eyes.
No, maybe I'll do 60. Ha! Just because I wanted to be defiant a little bit.
Wow, this is because look at mine.
Beautiful.
I need to send up with that.
Perfect. All right, so we got 119 point. What was the decimal? Like point
7.
7. 6 7 or 7 is fine. Believe me, I'm not too picky about rounding accurately. I assume you all know how to round from like 10 years ago. That I'm not really going to be taking off points. Like, no, I should have rounded down, not up. No worries. Okay. Oh boy, look at question E, everybody. What was the height of the ball when it made contact with the punter's foot? It's 2 feet, right? We actually just talked about that. And so when it hit the punter's foot, we knew that we're talking about basically the y-axis, because that's right when the ball started its path into the air. And so I want to know, what is that y-intercept, essentially? And if we just remember from the equation, we know that the y-intercept is always just the constant. But if I did want to calculate it, I can press second trace, and that first option value lets me type in any x value, and it gives me the y value instantly. So I can just select option 1, and it says x equals, and I can type in any x value. And we know for the y-intercept, what's the x coordinate everywhere on the y-axis?
0.
It's a 0, yeah. So to find the y-intercept, we make the x a 0, press enter, and we see 0, 2, right? So the football started 2 feet above the ground when it was kicked. I'm learning so much. This is awesome. It's like I used to be a physics major or something back in college. 2 feet. All right, what was the ball's height when it had traveled 100 feet downfield? All right, whenever it gives you a number, like this, 100 feet, it's asking what was the height when it traveled 100 feet downfield? Is this 100 going to represent the x or the y on our graph? That 100 feet, is that talking about your x distance or your y distance? Your x, good, because that's the horizontal. It's saying, hey, down the field, when x is 100, it's saying what is the height? And we know height was y, so it doesn't know what y is. So it's saying, hey, when x is 100, what is the y value? And guess how we can do this really, really easily? Same exact thing we just did, right? We're given an x value, and we want to find the y. Just press second trace, and that first option for value lets us type in any x coordinate. So what number do I want to plug in right here? 100, right, because it's 100 feet downfield. 100, enter. And how high is the ball? How many? Oh, I thought you said 1.
Yes, one.
1 and 20. Sounds similar, maybe. So 20 feet. All right, so when it's 100 feet down the field, the ball will be 20 feet in the air. Yeah.
What button did you press to get that X again?
So second trace, right? The calculate menu that you get everything from, and it's just the very first option, value. And so you just hit enter, and it already has a blinking cursor saying, hey, X equals, and you can type in any X value right then and there. So I just typed in 100, hit enter, and then it gave me a Y value of 20. So there's my point 100, 20. And so I can say for part G, how far, or no, this is for F, I'm sorry. The ball's height would be 20 feet. But it's 100 feet downfield. Hey, 100 feet, isn't that into the end zone already?
No.
No. What do we measure football fields in?
Yards.
Yards.
Just 300 feet.
Yep. All right, G says how far downfield does the ball travel when it reaches a height of 30? So this is similar to F, but we're actually swapping the two values that we're looking for, right? Because it says how far downfield, that's the X. So I don't know what this is. It's asking what is the X? How far down the field has it gone? I don't know the X. When it reaches a height of 30, but we know height is Y. And so this time it's saying, okay, Y, when Y is 30, what would the X be? Now to do this, whenever we know the Y coordinate, but not the X, we don't have a fancy button we press. This is where I have to make a second line and we find the intersection, just like we did with the 7 feet. Remember to see how close the one defensive player had to be when he could jump 7 feet in the air? Same idea. But now the ball is going to be at a height of 30. So I'm going to go back to Y equals, go down to Y2. If you had the 7 in there, you can just clear it out. I'm going to type in 30. So it's saying when the ball's at a height of 30, how far did it travel? So I hit graph, and there's a line that hits it. And, well, how many times will the ball be at a height of 30? 2 different times, right? Once going up, and then again when it comes back down. So what do I use to find this? Do you remember what option we choose? Yeah, we just want to find the intersection point. So let's practice doing that again. Second trace, go down to intersect, hit enter. And this one, there's no left and right bound. It just says what's the first curve or what's the first line that I'm finding the intersection of, hit enter. What's the second curve or the second line that I'm trying to find the intersection of, press enter. Then your guess, this is where the guess is important, because if I go to the left or if I go to the right, it's going to give me 2 different answers because there are 2 different intersection points. So here's where the guess is just letting the calculator know, hey, I'm interested in finding this one. Hit enter. And one intersection point or one time when the ball will be at a height of 30 is when it is 32.9 feet.
Can't they just be 33?
Yeah, you can say 33. That's fine. So we got 2 different answers here. We have at 33 feet and that's a bad angle. Can you find that other intersection point, everybody?
I already found it.
I already got it.
What? Fancy folk. So again, to do that, press second trace. Intersect, because we're finding the intersection. Enter. And first curve, enter, second curve, enter, and then guess. Just get it close to that other intersection point now. And we got 85.1. Make sure everyone else, did you get 85? Yeah? So 33 feet and 85 feet. So it's going to be 30 feet high on its way up to the top, and it's going to hit 30 feet again on its way back down toward the ground. Finally, this is just a kind of a common sense question. Why did we use the quadratic equation instead of a linear equation to represent the path the ball traveled? What would happen if we represented the ball's path with a line? Yeah, what would that mean the ball is doing when it was kicked? Right? So here's a quadratic, like this. Here's a linear equation. Why is the one on the right bad to represent the path that a football travels when it's kicked? Yeah, no gravity. What would happen? Can you imagine if someone kicked the ball and it just kept on going straight up in the air forever and ever and ever? That'd be crazy. Maybe on Mars that would happen. Not here though. So that's why the parabola is a better choice. It shows it going up and coming back down. All right, what do you think? Quadratics, actual applications of it, makes you use to find certain things. Kind of fun, right? I know, super fun. Okay, I want to go through one more with you, and I'm just going to let you try some on your own. So please turn the page. All right, suppose you work at F. Bender's car insurance agency. Fender Bender.
Mm-hmm.
It's funny, right?
Mm-hmm.
Yeah, thanks. And so you're working for an insurance company, and your company bases its rates on the likelihood of someone having an accident depending on their age. So a younger driver is more likely to have more accidents because of their inexperience. Would any of you agree? A first-time driver, chances are they're going to make a few more mistakes than someone who's been driving 10 years. Any of you in that boat already? Anyone have their license already? Yeah. No accidents yet? Thank goodness. So generally you start out, you're not that good of a driver when you get your license. But what happens as you drive more and more over the years? Are you more likely to get in an accident, or are you less likely to get in an accident as you get older over the next 10 or 20 years? What do you think?
I'm willing to debate that it's older.
Oh my gosh. 10 years from now, are you going to be old people? Be careful, Gavin. When you're twice your age, an old man like me, are you going to be okay? Generally, 20 years after you've been driving, you're pretty good. You've been around the block. You know what's going on. You've been in different scenarios. You're going to be a better driver. You're less likely to get into an accident. All right. And so then your insurance rate will go down because it's not too likely you're going to get into an accident. But then as you reach much older ages, not just older, but much older ages, why would the number of accidents start to increase? How old are we talking about here? 67, dude. 70s, 80s maybe? Anyone know any 80-year-olds who still drive? I did. I had a grandma. Yeah. My wife's grandma was still driving at 80, and that was not good. She caused a truck to flip over because she pulled out when she should not have been, and oof. Oh, and she was driving a scooter, by the way, at that point. Still not good. Yeah, very dangerous. On the sidewalk.
It's even worse than a car.
I know. All right, so even then when you're really, really, really old, why would you get into more accidents at really, really, really old ages?
Because you forget stuff.
You're forgetful. How about your reflexes? Are you as quick to react to things? No. How's your vision when you're super duper old? Can you still see things perfectly? In general.
You have glasses.
In general. Jeez.
Very sad because it's difficult.
Gavin.
I'm sorry. Math time.
I'm going to tell on you.
To who?
Your mom. And be like, Gavin made fun of me today. No, I'll be like, my dad can beat up your dad. He couldn't. All right. What? So this company's research shows that the age that you are versus the number of accidents can be represented by this equation right here. And we want to know how many accidents per billion. So when you say the number of accidents you can get, it's number of accidents per billion kilometers driven. Because like if you've never driven a car anywhere, is there a chance that you could have gotten into an accident while driving if you've never actually driven? No, right? That you can't get into a car accident while driving unless you actually are driving. But the more often you drive, even if you're a really good driver, just the more time you spend on the road, there's more and more of a chance that you could get into an accident. And so that's why this number is based on the number of accidents per billion kilometers driven. So if it's like 300, that's not saying you're going to get into 300 accidents. It just says if you were to drive 1 billion miles over your lifetime, chances are, based on that age, you would get into this many accidents. So that's kind of how that's worded. So how many accidents would you expect for a 70-year-old driver? So let's type in this equation into our calculator. Let's go back to y equals. We can just clear both of these out. We don't need any equations in there. Go back to y1. 0.04x squared minus 3.6x plus 100. And then we hit graph, and oh my gosh, our window actually still works. That's crazy. That often won't happen. Usually we would have to resize the window. All right, so there's our parabola. And if you look at this, this kind of shows you, remember, age is the horizontal axis. Number of accidents is the vertical or the y-axis. So it kind of shows the older you get, the less accidents you'll have. But then eventually, once you get too old, then the number of accidents you'll get in kind of starts picking up. Does that logic kind of make sense to you? Why it's this parabola shape? You have fewer accidents, then eventually you're getting too old and you start getting in more accidents, or the likelihood at least. So how many accidents would you expect for a 70-year-old driver? All right, so 70, that's an age. Is age going to be the x value or the y value? That's your x, your age. All right, so when x is 70, I want to know how many accidents, which is the y. So we need to find the y value when your x is 70. Yes, Brenna?
Can I have the window coordinates again because I accidentally ruined something and I had to reset the calculator.
Can you try to find it yourself? Because that's part of the skill that I'm working on teaching all of you. That's what you're going to have to do on the test. I'm not going to tell you the window. You have to figure that out yourself. So that's an additional skill for you. So go ahead and try it a little bit, and then if you can't get it, then I will definitely help you out still. What's up?
If you want to like do that accent, you don't have to.
I know. I just didn't want to give people too much info. Trace and then type in the number. All right. So when x is 70, what is the y? So I can do second trace. Value is the first option. Hit enter. 70. And right there. So a 70-year-old can be expected to get into 44 accidents. Now remember, that's how many accidents per if they drove 1 billion kilometers. Gavin. It's not saying that 70-year-old, which my dad is actually 71, that he would get into 44 accidents that year. No, it's saying if he drove 1 billion kilometers, it would be likely that he'd get into 44 accidents.
How do you get into 0.4 of an accident?
Good question. All right, so then 44. 44 accidents per billion kilometers driven.
So, how many accidents have you done?
You're 0, actually.
I don't believe that.
0 accidents. I've never been in a car accident in my life.
Do you still have it?
I owe it all to Need for Speed and Mario Kart. For real, like I remember driving down to Milwaukee when I used to teach down there, and I think I was on the phone. I know I shouldn't have been. That's dangerous, right? And I just had one hand on the wheel, and I was in the right lane, and a car totally didn't, for some reason, just swerved into my lane, and I totally like Mario Kart. I was like whoosha whoosha, and like just zigzagged right out and around and got back on there without any accident. I'm like, thank you, Mario. That's right. Like that was honestly the first thought in my head was thank goodness for Mario Kart, because this was when I was playing it on the Wii with the actual steering wheel. So I was used to actually turning to control my Mario Kart. And like the first thought in my head was really, Mario Kart saved my life.
Do you still drive a turbo Saab?
I do not drive a Saab any longer.
What do you drive now?
A more family-friendly vehicle, as I have 3 children. What would be considered a safe? All right. First off, I know some of you may have calculated this already if you've been working ahead, which is totally cool. But what do you think? Guesses. Do you think a 16-year-old driver is safer or an 80-year-old driver is safer?
80-year-old.
16, man. More fresh.
What?
Yeah, but at the same time.
Yeah, you just got your license. You know you're going to be showing off. You're going to be, putting the pedal to the metal. You want to be like, yeah, it's got a license. Look how cool I am. Yeah, but I didn't damage the car, so it was okay. There's my dad's. All right, so how do we determine this? Which driver is safer? What information should we look at? Maybe the number of accidents? Just off the top of my head, maybe? Mr. Carlson, what's safer, a 16-year-old driver or an 80-year-old driver? Who's a safer driver, 16-year-olds or 80-year-olds?
Oh, yeah. That's a tough choice.
Right? All right, so let's...
I would have gone with 16 because I think 80, you're starting to slow down a bit.
All right, so let's see. When your age is 16, you're going to get into 52.64 accidents. That's an average. That's why it's a decimal point, right? You can't really get into 0.64 accidents. Maybe like on the day of your birthday, you're like just about to swerve right at that moment. So you're like at 0.64 of the way into another accident. So that's 52.6. And when you are 80,
68.
oh, I can't even see it on my graph. What do I need to do? Window. Let's make that Y max bigger.
Question though, before I go get my water.
Let me
What is that app?
TI Smart View,
I know, but where'd you get it?
90-day trial.
Oh.
I know, but I also did price it out, so we're gonna get some of these. I did for our whole department, because isn't this way better than what I used yesterday? Everybody,
Yeah.
it's pretty cool, right?
I don't know. I kind of liked your thing.
It was so stupid. It was so glitchy yesterday. Carlson. All right, so who's safer, the 16-year-old or the 80-year-old? Everybody.
I still say the 80-year-old.
The 16-year-old, right? Because they get into fewer accidents. The 56 versus 68 accidents.
What? After every sentence.
Dun, 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 dun. So the 16-year-old, because they get into fewer accidents per billion kilometers driven.
45.
All right, at what age would a driver be considered the safest? Well, how can I use this graph to determine a safe age? The vertex. What does this vertex indicate? That's the minimum in this case, right? Because it's a lower point. And isn't that bottom going to be like the lowest insurance rate? that's when your insurance is going to be the absolute lowest that you're paying because you're not that likely to get into an accident. So whatever age that is would indicate the safest age to be a driver. So let's go ahead and find that vertex. All right, see if you can find this on your own. I'll do it up here. Minimum.
What?
I don't know, you just laughed at me and looked at me, so I looked at you.
Oh, I said safest age is your age.
Is it really? 45? Are you kidding?
Would you probably like 24 at the most?
24. This is kind of funny. A lot of times, since I've been a teacher, and I ask my high schoolers, how old do you think I am? I'll get anything from like 22 to 48. Like, can you really not judge age at all? If you ask like a 6-year-old, that makes sense. I mean, my daughter will tell me I'm 106.
I mean, you could be like 30.
It could be. I could be 30. What do you think? 45?
Yep.
Not until next year.
Solid 66.
66. Whew. I can retire then.
Yeah, good.
All right, so 45, this would be the age that has the lowest insurance rate, or the lowest number of accidents, I mean. And so they're only likely to get into 19 accidents, and that's the lowest possible number. That'd be when you're at age 45. So 45 years old.
Is it 4 scared of 5? It's so far away.
I'm writing with the mouse. Okay, let's see you do better
Okay.
later. That's because I can't see with my old man eyes, right? It's my arthritis is kicking in. All right, your company does not want to insure anyone that will have an accident rate of 83 or more. What would be the age limit? At what age are they going to be like, no, you're too old. We can't insure you. Right. So that's when accidents are at 83. That would be the Y value. So I'm going to graph another line at, 83? I'm going to do 83, graph it. And what do I need to calculate here? What's that menu option that we choose for this? The intersect. Yep. Find the intersection of these two. Now, I do have two options, right? I have one intersection on the left. But do you think that I want this intersection point where I should tell the insurance company, hey, don't insure anyone age 5 or younger. They're not going to be good drivers, right? Does that make sense in this context?
Yeah.
For this word problem? Of course not, right? Because they've got their like cozy coupe, the red cars with like the yellow roof and the honky horn that they move their feet in, the Flintstone toy car, right? They're fine.
Yeah, but they're going to need insurance.
As long as they don't play with those by stairs or anything, they'll be good. So let's find the other intersection point. Oh, by the way, little shortcut for you since you're all like professional graphing calculator users. Sorry, my memory's going. Instead of like pressing the down arrow, down, you can just hit the number of the menu item you want. So if I want the intersect, which is at option 5, I can just press 5 and boom, it selects that. First curve, second curve, guess. I'm going to now move my cursor over to here. And look how it gives me a battery level for my calculator.
I was just connected to like your actual computer.
Stop talking. It's plugged into the wall.
Well, ours aren't.
There should be a feature where the calculator runs out of power and closes out every single tab on the keyboard.
All right, so when X is 85, so basically that's the oldest age. So this insurance company will not insure anyone ages 85 and older because they're just going to get into too many accidents. They think. And again, those are averages, but too bad. Go with someone else. Okay. So that was all my detailed explanations and versions of everything that you can do. What I want you all to do now, and if you'd like, you can even work with a partner, just social distancing protocols. Don't be having your masks off and don't be coughing on each other, please. But I'd love it for you to collaborate and work on these next 4 questions together on your sheet, okay? So you got half an hour of class time. It's practice time.
Is this our homework?
No, it's not your homework. That's your classwork because it's class time. Work in class is called classwork. Work at home is called homework. Big difference. So you've got 4 problems that I want you to work through. Right now, you can work on your own. You can just share your answers with somebody else. If you're confused, talk to each other. Right? It's so great that we are all in the same room that we can still talk to people if you want.
Mr. Wilson.
Yep. Oh, but he didn't. I think his hand was up like a millisecond too late. All right, so get some practice and have some fun.